Hi everyone. So far, what we have discussed in this course on in this chapter on cellular concept is that as a cellular operator, how do you go about dividing a big area into cells? And we decided how many channels. I mean, how do you actually ensure you choose your cluster size n? Okay, we said that the cluster size has a direct dependence on carrier to interference ratio, and we said what should be your choice of cluster size. The next question, we also very briefly discussed how to assign channels. But what we did not discuss is that if let's say you assigned S channels to a cluster of N cells, each cell getting K amount of channels, so number of channels assigned to each cell is K, and to a cluster you are assigning S channels. How many users, practical number of users, can you actually support? We discussed in a very vague manner that if I have S channels, then I can support K users simultaneously. Okay, so that's the question that we'll be answering in this part of the lecture. So we'll consider an FDMA system, meaning your system has many channels available and each user gets one orthogonal channel as a resource. He's going to access the channel when he's making a communication. And the analysis that you are going to do now will be mainly applicable for speech communications. Okay, so this was an analysis which was used in the first generation, the analog mode, the analog AMPS systems, the analog communication systems. So now the questions we need to answer is, if I give you the number of channels, how many users, how many subscribers can we support? The next question is the number of subscriber count, I'll call it as U, and the number of channels as C, do they have to be same? Okay, or as we will later see, the user that you can support will be much greater than the channels available. So this question is answered by what we call as a trunking theory. It's a theory we borrowed from probability and statistics, and it's answered by that. So now the simplest problem is, let's start with the worst case design. Worst case design assumes that every user in a cellular system is going to make a call simultaneously, and the calls will be made all the time. So in that case, if every user is making simultaneously, at maximum I can only support the number of users I can support will be exactly equal to the number of channels available. Okay, but now this doesn't make any sense at all. I mean, you can never have a system where all the users will be simultaneously using it. So one classic example to compare the situation is to compare the number of hospital beds in a city. A city might have 1 million population, but you might have only 1,000 hospital beds. The reason being that not everyone falls sick simultaneously. Okay, so again, in situations like a pandemics, of course, now what we are facing is that condition may be violated. Okay, so now you need to understand how many of them are actually going to fall sick. So there will be a statistical behavior model which will characterize the number of people who fall sick. So similarly, we can also analyze how many people are actually going to make a phone call. We need to understand some kind of a statistical model. So before that, first we discuss the worst case model, so which is everyone is using, then I can only support C users. That's obvious. If everyone is making simultaneously worst case this scenario, then I will need C users for it. C channels to support C users. Okay, and I can only support C users. Now we will go for a best case design. The best case design, what I am going to assume is that there are U users in the cell. Okay, and we need to find how many number of users can we support. I have given you C channels. Now it is given that each user is not going to use the channel for throughout the day. I am trying to find in one day how many calls can we put through. Okay, can the systems and the subscriber and the operator serve the community of some people? How many people he can serve if each one of them is going to make a call only for m seconds? He is going to talk only for m seconds. Okay, so since he is only going to talk for m seconds, I can simply time multiplex each user, and I'll assume that each user is going to make the call sequentially. So first guy makes a call after m seconds, second guy makes a call after m seconds, third guy makes a call, and so on. If they do that, that's like the best case scenario. So then all I need to do is I have to divide 60 seconds by m. Okay, this will be the number of calls in a minute. Okay, so in 1 minute you will find the number of calls, and that multiplied by 60 will be number of calls in an hour, and multiplied by 24 will be the total number of calls in a day. Okay, so that is if the user uses one channel, each user is using one channel. But if he has C channels, I can support this many number of users. So this is a really a huge number. Okay, for small values of m, assuming m is less than 60, this is a really a huge number. Again, this is the best case design. There is no way users are going to make the calls sequentially, one by one. Okay, so obviously then the best way to understand is that as an operator, what you need to do before you go on to decide how many channels should I assign in a cell for a base station, how many channels should I assign, you have to understand the statistical nature of the people in the cell. What is the probability distribution with which they are going to make a call? What is the duration for which the call lasts? Okay, and the more important thing is, once it is statistical, there is a finite probability that the calls will be lost. Okay, you are going to get calls blocked. So then we need some kind of parameters and some simple, any engineering problem needs some simple mathematical analysis. Okay, so how do we go about analyzing and solving this problem? So what did we do right now, just to quickly refresh, is that I'm going a little slow because I didn't cover, this is the new topic that I'm going to cover now. The previous lectures I've already discussed in the regular lecture hours, so that's why I went a little fast. But this one I'll go a little slow. The worst case design, each user makes use of the channel, all the users are going to simultaneously make use of the channel, which means they're going to make simultaneous calls. Then I can only support C users. And we said that's never possible. We gave an example of hospital beds versus number of residents in a city. You design number of hospital beds keeping in mind that, okay, everyone in the city is not going to fall sick. If they fall, yes, of course, we'll run into problems. So, which is what is happening in a pandemic situation. Okay, so then we will of course need to increase the number of beds. That's an obvious situation, but we will never encounter such a situation. Which is why I can actually have your user count to be much greater than the number of channels. Okay, so in that case, your natural question is, how can you say if the number of users is more? Yes, it is more compared to the channel. What number is good enough? How do you say that, okay, if I'm going to have more users than the channels, how can you guarantee that I'm going to get good service? So that's what we'll be analyzing in this lecture. So the theory, how many channels are sufficient in a cell, and on what basis does an operator decide that you have to give so many channels in a cell? Okay, and how can you say how good the service is? On what is the metric for it? Okay, so this is what we'll be discussing in this lecture, and the theory which explains this is what we call trunking theory or queuing theory. It's a very big topic in queuing theory. Trunking theory is what we'll be calling right now. So to first understand, before we start with the mathematical analysis or the equations, we go to the equations, we should understand some basic definitions that are used in the trunking theory. The word that's often encountered in trunking theory is called traffic. Traffic or traffic intensity, it tells you how occupied a resource is. Okay, so for example, if a channel is occupied 80% of the times, then you will say the traffic intensity is 0.8. Okay, now the units, it's a dimensionless quantity, it's a fractional occupancy, it's a dimensionless quantity, so the units for that is Erlangs. Okay, the other way of defining traffic is also number of, for example, in cellular phones especially, it's number of call hours per hour. So that's also another definition, call minutes per minute or call hours per hour definition. So how many calls, see, we don't care about how many calls are made per an interval, per unit time, but what is the duration of the calls as well? How many 10-minute calls are made per hour? How many 1-minute calls are made per hour? So that metric has to be captured. So that is what we call as traffic. It's a hour per hour dimensionless quantity. Okay, so here it's given, if users in an area make 10 calls per hour, each lasting 3 minutes. Okay, so then what is the traffic offered? The traffic offered will be, you have to multiply the 10 calls per hour, and each is 3 minutes. So it is actually 10 3-minute calls per hour. So 10 3-minute calls per hour. Okay, so 3 by 60, you will get its dimensionless quantity of 0.5 Erlangs. Okay, this is again 0.5 Erlangs. So now to mathematically quantify, we'll start with the definitions now. H will be the duration of the call or the hold time. It's often called the hold time, is the time for which the channel is held Okay, it's not accessible by anyone else, or the channel h is called the hold time or the duration of our call. Lambda is what we call rate, number of calls per unit time. Then the traffic offered per user will be the duration of the call multiplied by the call rate, number of calls made per unit time. Multiplied by the duration of the call will give you the user traffic. This is called the per user traffic. Okay, this is the traffic offered by a user. The next thing is, if there are u number of users in a cell, then the total offered traffic by the users is simply u times AU or u into lambda into h. Okay. Now if I have C channels in the system, in the cell, each cell is having C channels, then the traffic per channel. So this is actually a traffic, the overall traffic in the cell. In the base station, one base station will be able to, this is the offered traffic to the base station. We are saying, okay, look, this is the demand the users are requiring. This is the traffic you have to supposed to offer. So that's what it's called, offered traffic. Okay. Now offered traffic per channel is you have to divide it by the number of channels. So this is the offered channel per traffic. Now there is a word called carried traffic. Carried traffic is nothing but, so you have C channels, and if I say each channel is occupied x% of time, so 100x is the percentage, so it's occupied by x fraction amount of time. So then each channel will be occupied x for x units, so then the traffic per channel is x Erlangs. So since you have C channels, the total traffic for all the channels is x into C. Okay, so this is called carried traffic. Okay, see, this is the offered traffic, meaning this is what the users are demanding, but whether the channel can handle it or not, that's called offered traffic. So that's called carried traffic. The maximum carried traffic can never exceed C, because the maximum, because your channel, if it is occupied all the time, then the traffic for the channel is going to, per channel is going to be 1, and if you have C set channels, you will have, C is the total offered, carried traffic. Okay, so you cannot, even though your offered traffic can be higher than C, you will not be able to provide it. It means that, what it means is that if your offered traffic, if user traffic demand, the demanded traffic by the users is very high, then you will not be able to meet it. When I say high greater than C, then you will start having a lot of missed calls or dropped calls. So we'll talk about that. Okay, so this is just the preliminary definitions which we'll be using in our analysis. The two more important definitions is, A is what we call offered traffic, C is the number of channels, or this is the maximum carried traffic. Okay, I won't be using the word carried traffic. C will be your trunked channels, total trunked channels assigned to one base station. Okay, A is the traffic, the average offered traffic. So these two are very important parameters. A high offered traffic means that I can have many calls per hour. Okay, so it's good, a good number. Okay, for a minimum value of C, C is like a resource. This is the number of channels available. For a limited values of C, if I have a very high value of A, then it's really a good system. Okay, so now we know that obviously if the number of users are going to be greater than the number of channels, some calls are going to be dropped. That's obvious thing, because you can't cater to every user. If every user simultaneously makes a call, then we are going to have a call being blocked. What we are interested in is finding out how many calls will be blocked. Based on that, we will derive a performance metric. Okay, so what we are interested in is P block. How many calls will be blocked? And the number of calls blocked will obviously depend upon the number of channels you have and also the traffic. What is the traffic that I'm using the word traffic now, but by now you understand that what does it contains information about how many calls the users are going to make, at what rate they are making the calls. It depends on that. Okay, so these are the two important parameters the blocking probability will depend upon. So to analyze this, we are going to use the theory which was developed by Erlang, a mathematician named Erlang in 19th century. We'll be using that. And to mathematically analyze this, we will make certain assumptions. Okay, to derive, I'm not going to derive an expression, I'll give you an expression. To get that expression, we'll have to make some assumptions. Now, the users are going to place calls at different times, and all those times at which the user plays the calls, they are all statistically independent. They are not dependent events. One user, when he makes a call, and the other user, they are completely independent of each other. Now, if let's say all the available channels are occupied, and when the new user is going to place a call, then that call will be blocked. Okay, that call will be blocked. Now what happens is, after some time the user can again try to make a call request. At that time, that call will be treated as a new independent call, a new request to the system. So between one call and the other call, even the calls which are blocked and you make a new request, they are all statistically independent. You treat them as new calls every time. Okay, and the more important thing here is the duration of a call follows an exponential distribution. So this is the duration of a call, which means shorter duration of the calls are more likely, longer durations of the call are less likely. If I plot the duration of the call t on one side and the probability random that I'm going to plot the duration f d of d, where f d of t, where d is the duration, then longer calls are less likely compared to shorter calls. And this used to make sense during the times when telephone systems were working, because telephone systems, the longer you speak, the more was your telephone bill. But today it's no longer valid. I think it's very common for people, especially to have very long phone calls in these days, especially with some social media accounts. I mean, especially the youth, you can never expect them to have shorter calls. Okay, and so, but still this model assumes that. So that's an assumption made by this model. So we'll go with that. Okay. So in the past, if you're going to make a longer call, it's going to be more and more expensive. So money was the motive. So therefore, shorter calls. Quickly you convey the information, especially between two elders. It's just an information conveying call, and you just terminate the call as soon as you finish what you conveyed. Okay. Because it was expensive. But now it's no longer that an issue. But we are going to make this assumption. It's historically used that way, especially for telephone calls, voice channels, and first generation communication systems, wireless systems, cellular wireless systems. So we'll do that analysis. So this system, where the calls follow an exponential distribution and the time of arrival of the calls is statistically independent, and each call, when it is blocked, when the user makes a new request, it is treated as it's treated as an independent event compared to the previous event. Okay, such a system is what we call as an Erlang B system. It's also called blocked call cleared system. So anytime you're blocking a call, you just clear it out from the memory, that you don't retain it. There is something else called blocked call delayed system, wherein when a user is making a call, a request for a call, when all the channels are occupied, you just put him on hold, you put him in a queue. Okay, so those are called blocked call delayed systems. But the cellular system is more of a blocked call cleared system, because once all the channels are occupied, when you make a phone call, if there are no available channels, then you get a message saying channels are occupied, try again later. So it's blocking your call. Okay, so it's a blocked call cleared system, BCC system, or an Erlang B system. Now the probability of a call blocking in an Erlang B system is given by this expression. Okay, A here is the offered traffic, okay, which is found by each user offers a traffic AU times the number of users in the cell. That will give me A. This is the average offered traffic in the entire cell. And C is the total number of channels assigned to each cell. Each base station is assigned C channels, and this is the expression. And that's also called grade of service. Okay, ideally you want a zero probability of loss. Every call that is made has to go through, but that's never going to happen, because the channel number is finite, but the users are obviously going to be much greater than the channel number. So you are going to have some blockage. Calls are going to get blocked. But what is that? How do you find that call blocked? So the simplest mathematical model that we use is an Erlang B system model. From that we compute this probability of blockage. So first, what you need to know here is two things. One, you need to know A, which is your offered traffic. Now this is entirely a statistical parameter. You have to find based on the statistical models you have for the users in a cell. So obviously, in the current times, with machine learning fully evolving, a machine learning algorithm will probably study the statistics of the users in a single cell. That's what it should be done, and my guess is it's already done. Okay, so a machine learning algorithm will study the statistics of users in the given cell. And then probably over time, the statistics might also change. So it will keep updating its models. From that, the two things you should know, the number of channels available you're already aware of, because your mobile switching center MSC will be aware how many channels it has assigned to this base station. Okay, so each operator will decide what is the probability of blocking or grade of service he can provide. So if I say 1% blocking probability, so I've given here is, if let's say an operator gives 20 channels and 1% blocking probability, then the average offered traffic is 12. So you can actually find either ways. I can support an average traffic of this much. If I give you blocking probability and the number of channels, you can tell what is the traffic you can support. Okay, so for a good probability, which is very, very low probability of error, which is 0.01, you can see that the offered traffic will be normally less than C. But if you increase your probability of blocking, I can actually have a much higher traffic than the channel number. In that case, your probability of blocking will keep on increasing. You will have more blocked calls. Okay, now this is a pretty complicated expression because it's a very nonlinear expression in terms of A and C. So for example, there are three parameters here: the probability of call getting blocked, the traffic, user traffic, and C is the number of channels. So if you know two parameters, the third one gets fixed. So if the operator starts with, okay, I need a certain blocking probability and I have so many channels, then I can, what is the user traffic I can support? You can find that out. Or if you know the user traffic, and if the operator decides I need a certain probability of blocking, then you can go back and recalculate what is the number of channels you need for that. Okay, so that's what it's used. And since it is a complicated expression, there are standard charts available called Erlang-B charts. So in case if I'm asking a question, I'll normally provide the Erlang-B chart to you. I'll probably upload it. You can take that chart to an exam. Okay. So for example, in this problem, what I've shown here, okay, so C equals 20 and 1% probability of blocking is nothing but 0.01. I just took this number from your textbook. So this is a value of A equal to 12. I can substitute in this equation. This is a very complicated equation to solve. Instead, you just refer to an Erlang-B chart. Okay, and get that value of A. So the Erlang-B chart will look something like this. I'm sorry if this is a little tilted. I'll just use this to explain it. On this axis, I'm plotting the probability of error. On this axis, you have the what you call as the traffic intensity. Okay, on this axis you have the traffic intensity. On this axis, in fact, for each value, this is for each value of channels. So here I've assumed C equal to 2, C equal to 3, C equals 4, and so on. We are plotting it for different values of C. Okay, this is a two-dimensional graph. It's only a 2D graph. Probability of error on this side, probability of blocking on this side, and the traffic intensity on this side. I'm thinking it might be a little difficult for you to visualize since I'm showing the graph in a slightly different way. I didn't get an image, but you can just open your textbook. I'll just give the interpretations. You can see your textbook and see this graph and analyze how to interpret the graph. So for each channel, each number of channels, I'm going to plot this graph. So if you see, for a probability of less than 0.1, probability of less than 0.1, you will always see your n, which is your C. This is the values of C here. Okay, and you can see the value of A, offered traffic A here, will always be less than C. At least the graph you can see visually here, it normally tends to be less than C. But if you extend this graph further, if you go for a higher probability of error, then yes, A might even exceed C. Okay, so for each values of C, I am plotting this values of probability of error for different values of A. Okay, so from this graph, I can, for example, let's say I tell you 1% probability, 1% probability of blocking. So you have to draw this line. In that line, you can find if I give you the number of channels here, so each channel is 30 channels, then you can calculate what is the value of A here. From this, you can calculate the value of A here. Okay, so I think it comes to around 20. So the value that comes to around 20. Okay, so you can see that normally you will also have a table wherein the values will be directly written. Instead of a graph, you can also be given a table, Erlang-B table. You can read from that as well. Okay, so that's it about Erlang-B system. So this is one way of characterizing it. The other way of characterizing whether how good how good the system can serve so many number of subscribers is called as Erlang C system or blocked call delayed system. So when all the channels are occupied, you will not block your call, instead you will delay it, you will put them in a queue. After t seconds, if the delay is still, if there is channels are still occupied, then you will block it. Okay, so instead of letting it exist, instead of immediately blocking it, you are going to block it after a delay t. Okay, so again the same assumptions hold in an Erlang C system as well, or the blocked call delay system as well. We'll assume the same things, times of which calls are statistically independent and all that. Okay, if your channel cannot be served, it is blocked, but instead put on hold till the channel becomes available or till a certain amount of time. Okay, again the duration of the calls and everything follow exponential distributions. The same thing is assumed here. Now the grade of service for the system, it's computed that a call will get blocked after waiting for t seconds. Okay, there is a unit of t is a time unit here. After waiting for t seconds, if the still channels are blocked, so channels are not available, then you block it. Okay, now what is the probability that the call will be completely blocked? A call is, which means the waiting time is 0, almost 0. So all you need to do is to find what is the probability that any waiting time greater than 0, you should just block the call. Okay, so then the probability that delay is greater than 0, that again the proof of this is not, again this is an engineering course, the proof is not very important. What are we going to do with this equation? As engineers, what does this equation, see, what is important to us is the assumptions. If these assumptions doesn't hold true, then these equations don't hold true. That's it. It's as simple as that. So obviously you should have a better understanding of the statistics of the users, the traffic offered by the users, and based on that you can estimate the probability of blocking. Okay, but this is for hand calculations. Like I always said, most engineering problems begin with a hand calculation and an intuitive understanding of the system, and then we rely on softwares, advanced softwares. Okay, so this is essentially for the initial mathematical understanding of the system, at least approximately how the traffic and the channel, the number of channels available is linked with each other. So C is also called trunked channels. Okay, since the theory is called trunking theory, the word C, it's called trunked channels. So in fact I didn't discuss this a little bit, the expression, because I didn't derive the proof of this. Probably I'll just spend one moment just talking about the proof of this equation. It's nothing here. This is nothing but what is the probability that all the C channels are occupied divided by probability of all the possible occupancies, so that will be like 0 channels occupied, 1 channel occupied, 2 channels occupied, till C channels occupied, sum of all that. So then you divide the two probabilities, you get the call blocking probability. So when does a call get blocked? When all the channels are occupied, right? So it's using that they derive this result. It's a very simple proof, but I thought it's not necessary for us. We just need to use this equation, and you have to use that graph, the Erlang V charts. Okay, what is more important is there are some very interesting intuitions, very interesting design rules which will be deriving from the Erlang V charts, which I'll discuss once we finish the equations. So similarly, the probability of blocking in a Erlang C system can be derived and shown to be this. The expression is pretty complicated. I will not be testing Erlang C in the syllabus. I'll only test based on Erlang B. So whatever intuitions we want to understand, we can gain it from an Erlang B system. So I'll not be testing here. Okay, for an Erlang C system, it's not something I will test. Okay, the next thing is again, what is the probability that a call is made to wait more than t seconds? So that is nothing but probability of delay greater than t. You can just use conditional probability here. Probability of delay greater than t given delay greater than 0 times. So this follows from this result. Probability of b given a times probability of a will be equal to probability of b. Okay, so this is one standard equation from conditional probability. We can use this equation to find the probability that a call is made to wait more than t seconds. The expression is, you can just see this expression. So if t is 0 here, that is delay greater than c, you get this expression, probability of blocking. Okay, and similarly the important parameter in Erlang C system, the important parameter is the average delay for the calls in the queued system. For all the calls, any call that will experience a delay of certain amount, because we said all the calls which cannot be served instantly, if they are, we don't block them, instead we put them in a queue. So what is the average delay that each call experiences? Okay, that's given by this expression. And the delay for a call in a queue, again, this is pretty intuitive. If you think of it, it will be simply I'm not spending much time on this because I'm not going to get involved with this. For the sake of completeness, I've just discussed this. Okay, Erlang C system. So the parameters of interest in an Erlang C system, of course, the probability of call getting blocked, and the delay that the calls experience in the queued system, and the delay for a call in the queue, the one which is not getting served, will be h by c minus a. H is the holding time. That's the holding time. If you see, h didn't figure in the expressions for Erlang B system, but in Erlang C system, it figures in. Because the amount of time you are going to delay in a queue depends upon the average duration of a call. So once the call is done, then you are going to give that channel to the new user. Okay, so it depends on that. So which is why in a blocked call delayed system, BCD system, the h will figure in the equations. So I will not be testing in this. I just wanted to present it. Main things you need to know just to understand is that in a similar way like in Erlang B system, grade of service is defined for calls getting blocked, and the expression is a little bit more complicated, slightly more complicated than an Erlang B system. The other thing to know is what is the average delay that the call experiences, and a delay for a call in a queue. So these are the three things which you should be aware of. Okay, so the next lecture